Thanks for the introduction. So today I'm going to talk about the work I have done during past few years on the formal synthesis of, let's say, hybrid system, both deterministic and stochastic. And so as you can see in the title, so the main, let's say, technique which I'm going to use is the abstraction. And I'm using actually two types of abstraction. So maybe some of you are not very excited about maybe one of the abstraction due to cares of dimensionality. So that's the reason we say, OK, let's actually add two types of abstraction. So we push the system in the continuous domain to actually make it as small as possible. And then we apply another type of abstraction, which is, which may have some cares of dimensionality issue. So what is this talk about? So I'm given a physical system with a model which can be represented using differential equation, ordinary, or a stochastic. And now I'm planning to design a controller code. So it's a controller that's going to be implemented as a C code, in order to control in a closed loop fashion, to control this system in a way that the output of the system at the sampling time satisfies some complex properties. So, and also, moreover, what I can handle in these techniques is I can actually handle the dynamics of the cyber components. By the dynamic, I mean if you have a hardware or if you have a software inside your digital computation platform with some dynamic represented by some discrete system, finite state machine, I can actually include that in my formal analysis. And I can design a controller subject to that modeling framework of the cyber system. So what is the specification here? It can be automata, infinite string, or temporal logic. So I'm not going to elaborate on those things. So these are well-known type of specification in the computer science literature. But if you are interested offline, I can actually elaborate and give you the syntax and also the semantic of this type of a specification. What is the main problem? So can we design algorithmically and formally? So these two keywords are very important, So we're going to design a controller in a push-button approach, completely automatic, but on the other hand, also formal. We don't want to provide something which is heuristic and you don't have any formal guarantee that the closed loop will satisfy the properties. So these are the two main features of these techniques, is algorithmically and as well as formally. So appropriate control software, which will be implemented here, providing this control signal such that the output of the system satisfies this given specification. So what is the challenge here? First of all, the dynamics is complex. Even if we are given a nonlinear system, for a nonlinear system, excluding this discrete dynamic, just look at the nonlinear dynamic. Even we don't know using control theory how actually design a controller in order to satisfy these type of properties. So, but here it's not only a continuous dynamics, I also have a discrete dynamics which make it even heterogeneous. So it probably is even more complex. So on the other hand, the specification also complex. I'm dealing with a logic specification. It's not anymore a stability or tracking or synchronization. It's more complex. So that's the main challenge in this technique. OK, so what is the benefit if, let's say, if we manage to do that? So I can actually develop a complex system which is reliable and at lower cost and time. Because if I can design a controller in a push-button approach as also being formal, so then I can develop complex system by just putting the dynamic in the computer, putting the property in the computer, and then we push the button. So what is the output is going to be the controller as a C code, which you can easily implement. And you have this formal guarantee that the closed loop will actually satisfy your property. So that's the main benefit of this technique. So, of course, many of you in this room working on the autonomous vehicle, so that can be one of the motivating example that you can actually synthesize the controller, which is a software inside the computer of the vehicle, and is in charge of controlling the vehicle in the obeying a speed limit and satisfying the or avoiding collisions and other things. OK, so what is the general methodology? I call it symbolic techniques. So in the first approach of these techniques, I am given a continuous dynamic modeling the physical part of the system, yeah? So this dynamic can be actually interconnection of several components, yeah? So you can see there is an interconnection going on, and the dynamic can be ordinary differential equation or stochastic. So then what I do, I push this continuous dynamic to another continuous dynamic. So I showed with the hat, such that hopefully I can reduce the dimension of the system, and it also can maybe reduce the interconnection topology. I go from a complex topology to a simpler topology, and I also can reduce the dimensionality of each component. So that's the first step. So this is an abstraction scheme, but I'm not providing a finite abstraction. I'm providing another continuous abstraction. But the system is going to be lower dimension at the simpler topology. So the second abstraction is I actually provide now a discrete abstraction of a simpler dynamic. So a completely discrete system representing this new dynamic. And then I compose this discrete abstraction with the abstraction of the hardware or software that comes from the cyber component. Remember in the previous slide, I say the cyber component can also be represented by some discrete abstraction or discrete modeling, finite automata. So I can actually compose these two, and this yellow box represent the overall dynamic of your closed-loop system. Let's say your cyber physical system, yeah? You have a physical, you have a cyber, so now you have an overall modeling framework, all in discrete domain, yeah? So now in the second phase, or in actually the third phase, what I do, we synthesize a discrete controller for this overall dynamic such that this closed loop, so those means composition, yeah? When I compose the discrete controller with the model in the discrete domain, the closed loop will satisfy those complex properties. So, okay, so what is the next phase? So now I need to refine the controller step by step to a controller which I can apply here, yeah? So the first phase, I refine the discrete controller to a hybrid controller for this abstraction, yeah? Not for the original. So, and if I apply this hybrid controller to this one, the closed loop will satisfy the same specification that this closed loop satisfies. So now, but I am interested to design a controller for this dynamic. So in the last phase, I refine this hybrid controller using this continuous map to a controller for a continuous dynamic, and I have the guarantee that this closed loop system will satisfy the same property as this closed loop system satisfies. Yeah. So in every step, I have this formal guarantee that the closed loop will satisfy the same property.
So the control software goes where? It's part of the discrete controller, right? So the software on the left is part of the other software?
So you mean this one, yeah? So this part, plus this part, plus this part, these are all gives me the overall controller.
The controller will be part of the software eventually, right? So why are they separated from each other, the software part and the controller?
Oh, so this is just shows the discrete controller that I designed for the discrete system, yeah? So, I mean, your question is, at the end, I need to have the software implementing a controller for this one, yeah? So the software is actually going to be, let's say the code will be implement this continuous map applying by feeding the measurement of the system, the first abstraction, and also the input signal that comes from this hybrid controller, yeah? But if you expect me to actually, the finalized controller to be in the form of discrete system, no, it's not that. It's not like that. So you need to compose all these elements, and then you have the finalized product as the controller. So, okay, we have three phases. So one is the abstraction, it can be finite or infinite, and is the key steps here. And now also in the second phase, we had the discrete controller synthesis, which we can use actually existing techniques in the CS community, yeah? There is already a 20 years literature how to synthesize discrete controllers. So you don't need to worry about that part. So, and these are some of the sample specifications that we can handle. So you can actually, you can compose all these properties, you can compose all these specifications, and you can come up with a very long property that you are interested in. And these techniques can handle. And the refinement is actually, all this refinement which happens here, there is a tie with how you actually provide the abstraction. Yeah? The refinement part will be defined by the way that you construct the abstraction. So they are related. So how to construct the first and the second abstraction? So that's the key question here. Okay, so for those of you who are familiar, we have two types of abstraction. I don't care if it's finite or infinite. Yeah. So one is called complete abstraction. So we showed using this equivalency between them. Yeah. So this is an infinite system. I construct another infinite system, which is somehow an abstraction of this, hopefully with a lower dimensionality and less interconnection topology. And then we construct another abstraction, which is actually finite. So if I can establish this type of equivalency between them, so now, which we call, actually, these are all called complete abstraction. So I have this nice property that if I come here in the discrete domain, do some analysis, game theory developed by CS people, I see if I can find this discrete controller for this finite system such that the closed loop satisfies some given complex property. So due to this equivalency which I established between these two, I have this if and only if result. There exists a hybrid controller here such that this closed loop is equivalent to this closed loop. Because the closed loops are equivalent, if this closed loop satisfies some complex property, so this one also will satisfy the same complex property. Yeah? And now, because of this equivalency between these two, so I have this first if and only if between these two parts, now I have this if and only if between these two parts as well. So if and only if there exists this continuous controller such that this closed loop is equivalent to this closed loop, and because this closed loop is equivalent to this one, so then you know that the final controller, when you apply in a closed loop, will satisfy your complex property. So feel free to interrupt me if you have any question. Yeah. Yeah.
So it's not really abstraction, but more transformation. When you have an abstraction, you expect something so it can't exist and control it only if it exists.
No, it's actually if and only if, and it's also yeah, it's an abstraction. No, I mean the way which I'm saying it's an abstraction. So in the sense that when we construct the abstraction, so what do I mean by an abstraction? When I establish this relation means what? For any behavior here, there exists a behavior here that are related or close by, and other way around. For any behavior here, there exists a behavior here that they're also related.
The specification is consistent with the discretization, right? Maybe that's
No, it may not be even consistent. The specification can come something after. So the abstraction can be a specification free. So
okay. Can I give you an abstract specification for the continuous domain?
yeah, you can give me a specification in terms of in the continuous domain, and then I try to synthesize a controller. I bring the specification on the finite domain, design a controller, and then push it back for the discrete system as well. Yeah. So the gridding approach, when you put a grid on the state space, the small size of the grid, that's the whole point, because you provide an abstraction which is a specification free, but at the cost of tolerating the curse of dimensionality that comes from this small size of the cells. Yeah. So that's the whole point of providing abstraction by discretizing the state and input set, is because that type of abstraction is independent of the atomic proposition that comes from the specification. Yeah. Yes. I mean, I haven't elaborated under which condition I can provide the complete abstraction. Yeah. If you can compute the complete abstraction, then you have this if and only if result. But your question is under which condition, under dynamic, I can actually provide this abstraction. So, yeah, I can elaborate on that. I will go and explain under which condition. So, if you have a linear system and it's controllable for type of a specification, actually there is an algorithm that you can construct the finite system that are exactly, they are equivalent with the original differential equation. Yeah. Okay, so you have all this if and only if. So now there is another type of abstraction which it's called sound abstraction. It's not complete anymore. And you see I changed the relation to now less than equality. So if I can establish this type of abstraction, so let's say if I come here in the discrete domain, I managed to design a discrete controller such that this closed loop satisfies my complex property. Because of the sound abstraction, I have this guarantee that then I have a hybrid controller for this system such that this closed loop also satisfies the same property. But I don't have the if and only if anymore. So if I cannot find a controller here, I cannot say anything about this system. Yeah, may exist, but I couldn't find using this abstraction. And the same thing here as well. So if you have a hybrid controller here, you have a controller here such that this closed loop satisfies the same property. Yeah. So is it clear? So, okay. So now let's go see how can we construct this abstraction, the first abstraction in the scheme. So I'm looking at these type of control systems with the state in Rn, U in Rm, and the output lives in Rq. So, and I have the set of nice, let's say, control actions. So I introduce this notation, which I will be used later in the presentation. So this notation means a state trajectory started from initial condition X under input signal U epsilon, and this means the corresponding output trajectory. Yeah, output trajectory provided by this state trajectory. Okay, so in order to provide the relation between two concrete systems, there is a notion called simulation function with the interface introduced by Antoine Girard and George Papas. They are saying, consider two control systems, sigma hat, which we call it abstraction, and sigma, which is the concrete system. They have the same output space. So assume we have these two suitable functions. One is V and one is K. So V, which define on the product of the state space of these two systems and goes to non-negative real numbers, is a simulation function from the abstraction to the concrete, and K is called an associated interface if there exist these functions, K infinity, such that you have these two conditions. So the first condition just telling me that the simulation function captures the distance between the output of two systems. Yeah? The first condition guarantees that the output of the abstraction and the concrete, they are close. Yeah? So you can guarantee the closeness between the output of two systems. So that's the first thing you need to have. The output should be close. The second one is just guaranteeing that if the output are close, they also remain close as time elapses, because the derivative of V with respect to time is bounded by these two summations. If I start close, I also remain close. Yeah? And we use this notation to say sigma hat is simulated by sigma, which means there exists a simulation function from the system sigma hat to sigma. And you already see, given x hat, the state of the abstraction, and the u hat, and the state of the system, this is going to be the input to the concrete system. So that's the role of the interface. So interface is telling me how can I actually refine the controller I designed for the abstraction to a controller for the concrete system. Yeah? And the theorem is just saying if you have a simulation function from the abstraction to the concrete, so you can bound the difference or the distance between their output value. So the output value are epsilon close. Yeah? You can bound the difference between the output of two systems. So this is the main difference between this type of abstraction and the classical model order reduction control theory. We provide an L infinity guarantee rather than L2 or rather than L2 guarantee, because now for the LTL, or let's say those complex specification I explained, we need to have the guarantee of the closeness of the output value at each time. So that's the main difference. And this is the interface function is just telling me what is the output for the input signal for the concrete system using the state of the concrete, the state of the abstraction, and input of the abstraction. Okay, so what is the application of this simulation function? suppose I am asked to design a controller for the concrete system in order to enforce some desired behavior. So I use the abstraction of the concrete using this notation, which means there exists a simulation function from sigma hat to sigma. And I use the abstraction, which hopefully is simpler in terms of the interconnection as well as the dimension. So then let's say we can design epsilon hat that enforce the desired behavior on the abstraction. So I use the interface to refine the input I designed for the abstraction to an input for the concrete system. And from this inequality, I have this guarantee that we have a quantitative bound of how I deviate from the desired behavior. Yeah. So this is the graphical schematic saying that if I can design a controller for this sigma hat, satisfy desired behavior, I feed the epsilon hat here to this interface, and also I get the feedback from my state and the state of the abstraction, and I can force the input to the concrete such that this output also is close to the desired output, which I was interested. So now in the compositional construction, I'm giving this interconnected system. I know how to construct the abstraction of each component with this relation. And now the question is provide conditions such that the interconnection of abstraction is also simulated with the interconnection of the concrete subsystems. So there exists a way of constructing the simulation function from this interconnection to the concrete interconnection. So then I can actually, I don't need to look monolithically. I just look at each subsystem, construct the abstraction, and I have the guarantee that when I compose them, it's going to be actually an abstraction itself. So in order to do that, so we need to change a little bit each subsystem. It's now a control system, a cube with internal input, which will be used for the interconnection, and external input, which will be used for the controller synthesis. Yeah. And we assume the internal inputs are partitioned as following. So you see, I have index I1, so it means the inputs, the internal input that will get interconnection signal from system 1 all the way to system I-1. Of course, I don't have interconnection from my system to myself, so that's the reason you don't have WII. So you can go all the way to the WIN. You have n components with we assume you can have interconnection between all of them, yeah? And similarly, we also assume the output has this type of partitioning. So which Yij for I not equal to j, we call them internal outputs, and Yii we call them as external outputs. Those are which are available even after the interconnection. And the same thing for the output function. So if I compose all these subsystems, so now the composed system has this state, which is the concatenation of a state of all the subsystem, concatenation, and the input is the concatenation of all the external input of the subsystem, and the output of this composition is nothing more than the concatenation of Yii of each subsystem. Yeah, those are the ones which is still available after interconnection. With this interconnection constraint saying that Wij is equal to Yji. So their dimension also should be the same, yeah, in order that you can compose them. So this is the new dynamic. This is the dynamic of interconnected system, and this is the output function of the overall interconnected system. So we extended actually the notion of simulation functions with system with internal inputs, because we need to have this notion for the interconnection of subsystems. So more or less the simulation function is defined in the same space, but in the interface. So now not only the interface get the information of the external input of the abstraction, it also get the information of internal input of the abstraction. So, and V is called a simulation function. Again, the first condition is saying that the simulation function can provide a closeness guarantee between the output value of the system and its abstraction. The second condition is saying that, so the derivative of v is actually upper bounded by this negative term plus 2 term capturing the mismatch of the internal inputs and also the capturing the size of the inputs that we feed to the abstraction. So just to summarize, again, the second condition also provides some kind of quantitative guarantee that if I stay close, I somehow remain close. Yeah?
One question.
Yeah.
So for unstable systems, h of x probably is going to infinity, h hat is going to infinity, and the difference is going to infinity. The right side should also be going to infinity, right?
So if h goes to infinity, h hat goes to infinity, so then the right-hand side goes to infinity. So
if the system is not stable, probably in abstraction we have to keep the unstable mode.
yeah, but so by the second condition, I'm actually providing this, I'm excluding what you are saying.
Oh, okay.
So the second condition is actually telling me that the Lyapunov simulation function is not exploding, yeah? So now I will go back. So these are the two conditions I need. But now your question is, how can I enforce the second condition? Because the second condition is not letting that scenario that you are telling me to happen. That controlling the systems, first of all, the output to be bounded and also to remain closed, yeah? So now I will go back to that. So for the linear system, I provide how actually to design this K to enforce that Lyapunov or simulation function to be, the derivative to be bounded by these terms, yeah? So which means at the end, I need to have a stabilizability property on the concrete system, yeah? The concrete system needs to be stabilizable. Doesn't need to be stable, but needs to be stabilizable. Yeah. Okay, so I'm given n system, subsystems, and their corresponding abstraction and the simulation function. For the sake of presentation, I assume this function here and the rho function here, rho internal, they are linear, yeah? So now we construct these matrices using those Ci and Di, which delta ij comes from this. Of course, the result for even non-smooth simulation function you can find in this archive paper. So, okay, so if there exists a vector mu satisfying this inequality, then this function, which is linear combination of the simulation function of each component, is actually a simulation function between two interconnected systems. So which means if this condition is true, then I actually managed to provide a simulation function between the interconnection of abstraction to the concrete system, and I know how to actually provide quantitatively the difference between their outputs. So, and this condition is nothing more than saying that the spectral radius of lambda inverse times delta is less than 1. For example, when you have two components, the condition boils down to this. D1, D2 is less than C1, C2, which means, if we go back here, means this negative term will actually contain this term which comes from the mismatch of the input. So it means this negative term is big enough that the effect of the mismatch between two inputs will not affect on the decaying of the simulation function, yeah? More or less. Yeah.
So it seems that if I understood it correctly, the abstraction also depends on the controller, right? You have K in the second condition. But
yes.
It's not abstraction independent of the controller. Yes, when we go to the construction of the abstraction, so when I construct the abstraction, the construction of the abstraction and the controller comes together, yeah? So it's not like I'm given an abstraction and I'm given a concrete system. Of course, you can always try to, if there exists such a K and such a function. I mean, in definition, we don't say which comes first, yeah? It's just definition. Given abstraction, concrete, if there exists a function, given abstraction and concrete. If there exists two functions satisfying this, then V is called a simulation function. But when we go into the construction of the abstraction for the linear case, we actually do both at the same time. I construct the abstraction, simulation function, and K all together in a geometric fashion, which I show later in the talk. So, okay, so now, okay, here actually, the construction of the abstraction in the linear case. So how do we construct the abstraction? This is a concrete system, and this is, assume this is the abstraction. Yeah, of course, I want to know how to construct A hat, B hat, D hat, and C hat. And we choose this quadratic or a square root of quadratic simulation function. So V is a simulation function from sigma hat to sigma with M positive definite and a linear interface if and only if these conditions are true. AB is stabilizable, and you have these algebraic equations. Yeah, this is a if and only if result. Yeah, for some PQS of appropriate dimension. So now, how to actually construct? Of course, I have some conditions, but how do we construct? So, this is, by the way, this is the simulation function, so which means you have a sound abstraction, so you know how to go from sigma hat to sigma. I haven't established the other way around. So can I also establish a simulation function from sigma to sigma hat in order to guarantee that the abstraction is a complete abstraction? So we have the if and only if result, which are explained in the beginning of the talk. So in order to establish the, let's say, by simulation or the complete abstraction, so then the condition become more involved. So now I need to add these 3 more conditions. So I have a still AB stabilizable, and the first 2 conditions are the same. So now I need to add these 3 more conditions. So if these are all satisfied, now I have a, let's say, complete abstraction, which means I can establish the relation from the abstraction to the concrete as well as from the concrete to the abstraction. And again, this is a if and only if result. Yeah. Okay. So, of course, we all know from the control theory, linear control theory, AB is stabilizable is nothing more than this. I mean, forget about the first condition. The first condition is related to the output should be closed, by the V function. So you can always enforce the first condition using the second condition. But the second one is nothing more than that comes from the Lyapunov function, yeah?
So P is something you select a priori? Some kind of mapping between the two that you have in mind? Are you searching for that?
So I will explain now. Oh. Yeah. How to construct P. It's actually this. So we use a geometric approach to actually construct A hat, B hat, C hat, D hat, together with those matrices which appeared in all those algebraic equations as the following. So all these sort of equations equivalent to those geometric conditions, yeah? So now you can use actually the linear algebra technique how to construct, for example, the matrix P. There is actually an algorithmic technique how using that geometric condition you can construct matrix P. So
you need to know the dimensions to begin with, right? And you decide on.
So you start from the lowest dimension, okay, and then you see if the condition is satisfied. If it's not, then you add another column, and then you check, yeah?
Until P equals identity.
I mean, of course, in the best case, you don't want n hat to be equal to n, because that's the whole point of the abstraction, yeah? So n hat hopefully should be less than n, that you will benefit from the abstraction. But I'm sure there are systems, in a case, as you mentioned, that the P will actually hit the full dimensionality in the sense that the abstraction, you cannot actually get rid of any of the state variable in your concrete system. And because it's if and only if result, so it means, okay, there is no other way. So, and this is the interface, how to lift the controller we designed for the abstraction to a controller for the concrete system. So that will take care of the lifting or the refinement of the controller, which I explained. Okay, so that's, yeah, this is the full characterization. So now this was the infinite abstraction, yeah? But now there is another step remain, and that's the finite version. So I provide an infinite abstraction, but now how should I construct the finite abstraction for a given or for a computed infinite abstraction? So the idea is very simple. You put a grid on the state space and the grid on the input set, Of course, the size of the cell of the grid should be chosen in a smart way. So now we go back to your question, which working on your laptop. So how to construct a complete abstraction? Yeah, you said, okay, it seems you should lose some information. So if your system has some type of a stability property, we can actually provide an abstraction with finitely many states, which you can establish this if and only if result. So, but your dynamic needs to be stable. So, and the idea is very simple. You just simulate the center of the cell. You see where are you landing. You put a transition in the abstraction from this center of the cell to this center of the cell. For all possible discrete input action, you repeat this process. And now this is the way you construct your finite abstraction, yeah? So you need to iterate for all the cells, for all possible finite number of inputs, and then you have a finite abstraction. Pretty simple, yeah? If your system is not stable, then you cannot have the complete abstraction. You have a sound abstraction. It is not if and only if result anymore, you have a sufficient condition. And because your system is unstable, what we need to do, we compute an over-approximation of the reachable set after tau second for a given input signal. For example, let's say my over-approximation is this. If it intersects with 6 cells of the grid, so I just put transitions to all of them, non-deterministically under the same input. So we are introducing non-determinism. And that's the non-determinism that we introduce that will prevent us from providing a complete abstraction. Of course, if one can compute this over-approximation in a smart way, you can actually end up with less non-determinism. For example, Murad has a work on mixed monotonicity, how actually compute the over-approximation of this cell if my dynamic has some nice property. So what they claim is you actually need to, if I remember correctly, just simulate these 2 points under some function that one needs to compute, and that, by that simulation, you can just draw a box, and your reachable set tightly is going to touch that box inside, yeah? So that's one way that it's very simple. You just simulate 2 points. After tau second, you draw a box, and that's the over-approximation of the reachable set. So we developed a toolbox, which is available. It's open source. To the best of my knowledge, let's say it's the only toolbox which generates an abstraction for a general nonlinear control system. I mean, let's be precise. It's the only toolbox which is being maintained currently. Yeah, there are other toolboxes exist, and they claim the same thing, but unfortunately, it hasn't been maintained for several years. So this is the only toolbox for general nonlinear control system. Generate the finite abstraction, and then also generate the controller for few simple type of specification. So now we are working how to extend the toolbox for more general type of specification. So, okay, let's provide an example. This is a concrete system, interconnection of 4 subsystems. These are the corresponding matrices. So if you look at the interconnected system, it's 10-dimensional, yes? So, and these are the corresponding interconnection matrices. So we applied the techniques. We managed to construct abstraction for each component, which is 1-dimensional, yeah? And what is the specification that we are interested to satisfy on the original concrete system? Always stay inside the set S and infinitely often visit region Ti. So we have 3 regions. So we need to always stay inside the set S and infinitely often visit region Ti. And these are the set being defined here. So we construct the infinite abstraction. We fed the infinite abstraction into a SCOTS, and then the SCOTS construct a finite abstraction, and then also design the controller. So you see this is the closed loop simulation. So the trajectory of a real system is always within S, which is this gray ring, and infinitely often visit box T1, T2, and T3. And this is the difference of the output value of the concrete system and the abstraction, the infinite abstraction. This is the difference. And you see it's always lower bounded by the theoretical bound that we establish. So this means that your concrete system
always satisfy those property up to this error. So it means I am in this set with this error, let's say 0.3. So it means I may go a little bit outside the set, but up to inflation of 0.3, yeah? Okay, I don't know how much time I have. Okay, so everything I explained for the deterministic system, we actually managed to extend to the stochastic setting, a stochastic hybrid system. I just passed very fast because everything goes very much the same. I'm given a stochastic hybrid system using this modeling. I have diffusion, I have reset term, and I have a vector field. And those are, again, Rn valued, Rm valued, and Rq valued random variables. And correspondingly, I use this notation to define the solution process. Yeah, I just go very fast. We can establish the same sort of simulation function between the system. In the stochastic setting, V is the same structure. The interface has the same structure. But now the conditions are slightly different. So the first condition is, again, the same. The simulation function should bound the difference of the output. So the output should remain closed, and the bound is given by the simulation function. The second condition is telling me also the evolution of the simulation function in the moment is also going to be bounded. Yeah. So you see there are some term appears here that comes from the diffusion part, also the reset terms. But you can just look at this as the derivative of the simulation function in the stochastic setting. I use the same notation to say there is a simulation function from system sigma hat to system sigma. And the theorem is saying that they expect the moment of the difference of the output value, I can always provide an upper bound. Of course, here I show, for the sake of a simple presentation, I showed it the first moment, but the result for the general K moment is in the paper, which is available archive. And here I provide the guarantee for the moment. So you may ask what the probability in terms of the guarantee in terms of probability. So we can actually, using this function, I can actually provide also guarantee in terms of probability, but then it's not going to be anymore for infinite time horizon. I provide the guarantee of the closeness of two output in probability only for a finite time horizon. Yeah. So again, the idea is the same. If I can construct the abstraction, I solve the synthesis on the abstraction, I lift the controller to the concrete system, and I have the guarantee that their output is closed, and this is again the same. And again, what is the compositionality result in this case? So again, we define a stochastic hybrid system, which the cube with the internal inputs, because we need to establish the interconnection, and the internal input again has been partitioned the same as before. The same thing with the output. The output are going to be partitioned because we need to establish the interconnection. And the output function is also partitioned, exactly the same as I explained for the ordinary differential equation. So now when we construct the interconnected system, the state is the concatenation of a state, input is the concatenation of external input, output is the concatenation of external output, which we showed with the YII for each I component. And now we have the same interconnection constraint. And these are the dynamic. The drift, the diffusion, and the reset term, which easily is the concatenation of all the components. So now what is the definition of the simulation function between two stochastic hybrid subsystems? So it's more or less the same as the stochastic simulation function between two stochastic hybrid systems. So now I have this extra term that comes from the internal input as well. So everything is more or less the same, yeah? The closeness between the output and under the evolution, they also remain close. So if we consider n subsystem, because everything is more or less the same, I go very fast, yeah? So, and again, I assume those functions are linear for the sake of simplicity, and now we construct those matrices, and now the theory is actually the same, exactly the same, yeah? If you have these conditions, if there exists a vector mu satisfying this condition, which is somehow a small gain type condition, then
the linear combination of the stochastic simulation function is actually a stochastic simulation function between these two interconnected systems.
So the diffusion terms have to be 0 somewhere for that to hold? Could you go back a couple of
No,
slides?
nothing should be 0.
No, going back?
Yeah.
So you have that trace done, right?
Yeah, it's there.
Okay, so you don't need that to vanish to be able to come up with this lambda term?
I mean, I assume this inequality holds, yeah?
But for that to hold, is there any restrictions on sigma?
No, I mean, you will see now for the linear case, there is no restriction. I mean, there is a LMI restriction, yeah, that comes from the diffusion.
Okay.
Yeah, yeah, that the diffusion and the reset term appears, but not anymore. Like, you don't need, I mean, maybe your question is, do I need to say it's bounded? Like, for example.
No, I was just thinking maybe it has to vanish when V is vanishing, but okay, I wasn't sure what that is.
Oh, you mean sigma should vanish at origin? Like sigma 0 should be 0? No. I mean, as long as this inequality holds, we are happy, yeah? But now your question is, okay, under which condition this inequality holds? Which for the linear case, I will show the LMI. Okay, so the small gain condition is exactly the same as the non-stochastic version. So now I am given a concrete system. So this is called jump linear stochastic system, yeah? So all linear matrices. And let's assume this is my corresponding abstraction for this concrete system. So now here, we define the simulation function to be a quadratic function. And now we have this result. With, unfortunately, it's not anymore like the non-stochastic if and only if. It's only sufficient, yeah? So I'm working on if we can actually extend it to make it if and only if. So V is a stochastic simulation function from this system to this one with the M positive definite and a linear interface if this system is stabilizable in the mean square sense. Of course, when I say stabilizable, you need to put the internal input to be 0. And these equations hold, yeah, between all these different matrices. And again, you may say, okay, how using these equations I can actually construct those matrices. So maybe before that, I need to also establish the bisimulation, means two-sided, a complete abstraction. So V is a simulation function from sigma hat to sigma. V hat is a simulation function from sigma to sigma hat if sigma is stabilizable and all these equations are satisfied for appropriate matrices shown here. And in order to provide those matrices which appears in the abstraction, first of all, these LMI hold if and only if sigma is stabilizable in the mean square sense. Yeah? If the system is stabilizable in the mean square sense, implies that this LMI should hold for some M positive definite and some controller gain K, and a positive number K hat. So now we use a geometric approach to determine those matrices that appears inside the abstract jump linear stochastic system, and with the corresponding matrices that appear in the simulation function as well as the linear interface. So these equations is equivalent to this geometric condition, yeah? So this is if and only if, but the abstraction, so I have the simulation function, or let's say a stochastic simulation function or a stochastic bisimulation function if those conditions are satisfied, yeah? So here I don't have if and only if, but for the geometric condition I have the if and only if between those type of equations and also these geometric conditions. And this is the interface which lifts a controller for a abstract jump linear stochastic system to the concrete jump linear stochastic systems. I don't provide the way of constructing the finite abstraction. You can find in those literature, but let me provide an example. So this is an interconnection of 4 subsystems. It's a 10-dimensional system. We managed to construct the abstraction, and now as you can see, the abstraction is 1-dimensional for 2-dimensional and 2-dimensional for 3-dimensional. Maybe we didn't manage to improve the dimensionality, but one positive thing is we managed actually to simplify the interconnection, yeah? So we actually managed to get rid of this self-loop. So it's a 6-dimensional, but actually it's 2 disjoint 3-dimensional. And we have this compositionality. We established this compositionality result. And now the question is, the example, can I design a controller to enforce the output of the system to always remain in between 0 and 5? So here, we didn't, so maybe another benefit of using the first type of abstraction is, if you know how to synthesize a controller for a given or computed infinite abstraction, you don't need to go to the finite abstraction, yeah? So if you say, I look at my constructed infinite abstraction, I know how to solve it without even resorting to the finite abstraction. You don't need to construct finite abstraction. Just use the infinite abstraction, solve the synthesis problem, and then use the linear interface to refine it to the concrete system. That's exactly what we did here. We didn't construct any finite abstraction. We used the MPT toolbox developed in ETH that works on the, let's say you do like set manipulation, yeah, in order to compute the invariant set. So we actually used the MPT tool without even constructing the finite abstraction, and we managed to construct a controller for the infinite abstract system, and then we refine it to the concrete system. And we have this is the theoretical bound, and this is the simulation bound that we computed. So before finishing the talk, I just want to give you an announcement. So we're going to have a seminar, Formal Synthesis of Cyber-Physical System. It's a Dagstuhl seminar series, which is going to happen in Dagstuhl Castle. So it's from May 14 to 19. This is going to be the largest event on just formal synthesis of cyber-physical system, with around 60 invited people, which some of you actually sitting here will get in a formal invitation letter to give a talk. And also the nice thing is NSF actually provide a support grant for the students, for the PhD students that are interested to attend. They actually provide money. So to go, and you just need to apply for the grant here. And thank you for your attention. Yeah.